All right, I'm going to just do a review, not a review. I'm going to do solutions, a video key for exam 1. So if you're unhappy with your grade or if you have any questions, this is your chance to kind of process through and go through which questions you got wrong and why. So question 1, which structure does the nitrogen have a -1 formal charge? So nitrogen is right here on the periodic table. It's in column 15, which means it has 5 valence electrons on it. So for nitrogen to have a -1 formal charge, it must have 6 things that go away from it to get to -1. 5 minus 6 is -1. So that would be any combination of 6 bonds and electrons, or dots and lines. So on this nitrogen, we have 1, 2, 3, 4, 5. So 5 minus 5, that formal charge is 0. On this nitrogen, 1, 2, 3, 4, 5. So 5 minus 5, again 0. On this nitrogen, we have 1, 2, 3, 4, 5, 6. So 5 minus 6, this is a good answer choice. On this nitrogen, we have 5 minus 5 is 0. So my answer for this one is answer choice 3. Okay. What is the hybridization of the central atom? So that is a carbon with 2 areas of electron density. So we would need one s and one p orbital. So this would be sp hybridized. So that should be this answer. Which of the following compounds has a molecular formula of C2, H6, and O? Sure. The first thing I'm going to do is just start counting oxygens, so because there's the least of those. So there's 1 oxygen in all of these. So check. Next, I'll look for the carbons. So there's 1, 2 carbon here, 1, 2 carbon here, 1, 2 carbon here, and 1, 2, 3 carbons here. So that one's wrong. 1, 2 carbons here. Okay. And now I'm looking for 6 hydrogens. So 1, 2, 3, 4 hydrogens. So that one's wrong. 1, 2, 3, 4 hydrogens. So that one's also wrong. 3, 4, 5, 6 hydrogens. So that one's probably right. Just to check here. 2 hydrogens, 4 hydrogens. So my answer choice is answer choice C. Sorry about my voice. It's flu season in DFW, and I finally got. So, okay, which is not a correct Lewis structure? So if we're trying to figure out which one of these is not a correct Lewis structure, let's see. This is kind of a tricky question. Sorry. Nitrogen comes with 5 valence electrons. And then hydrogen comes with 2, and fluorine comes with 7. So that's 5, 6, 7. So there should be 14. Usually the most electronegative is in the middle, unless it's hydrogen or fluorine. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is missing quite a few of the electrons that should have come with it. We should have 14, and we only have 1, 2, 3, 4, 5, 6. Let's see, that's 2, 4, 6, 8, 10, 12. Oh, no, that's right. Okay, 14. So that's the right number of electrons present. So then the next thing I'm looking at is formal charge. This nitrogen has 5 things. 5 valence electrons. We have 1, 2, 3, 4, 5, 6 things bonded to it. So 5 minus 6, that should be -1, but also that means that we have 2, 4, 6, 8, 10 electrons in nitrogen's shell, and that's not possible. That violates the octet rule, so that one's wrong. Or that one's right, I guess. So that one is not a correct Lewis structure, so that is a good answer choice. Now for B, let's look at this one. Carbon comes with 4 valence electrons. Hydrogen comes with 3 valence electrons. or 1 each, and there's 3 of them, and fluorine comes with 7. So this is, again, has 14. So we have 2, 4, 6, 8, 10, 12, 14. So that's right. Formal charge on carbon. Carbon has 4 valence electrons, minus 4 things is 0. Fluorine comes with 7 things, minus 1, 2, 3, 4, 5, 6, 7 dots in line. So this looks like a valid Lewis structure to me. Okay, let's see. Oxygen comes with, I believe it's 6, but let me just double check. Yeah, oxygen comes with 6 valence electrons. So 6 times 2 equals 12, plus 2 is 14. We have 2, 4, 6, 8, 10, 12, 14. So that's right. Oxygen's formal charge should have 6 things around it. 1, 2, 3, 4, 5, 6. So that one's right. Okay. And then this boron comes with 3. Oxygen comes with 6 times 3 equals 18. And hydrogen comes with 3. 18, 19, 20, 21, 22, 23, 24. So let's see. 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24. So that looks right. Boron 3. Formal charge has 3 things around it. Oxygen formal charge is 6 minus 2 bonds and 4 electrons for each of these. So this looks also correct to me. So I would give the answer choice being A. Oh, A right here. Okay, which compound is not a constitutional isomer of the others? So, I'm going to start here by counting up each atom. So we have bromine, carbon, and hydrogen. 1, 2, 3, 4, or all of them have 1 bromine. Normally, here, let me actually do it like this. I'll say bromine, carbon, and hydrogen. So all of them have 1 bromine. And then let's look at carbons. 1, 2, 3, 4, 5, 6. 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, all of them have 6 carbons as well. Now let's look at our hydrogens. I'm just going to draw a dashed line for hydrogen. They look like methyls, but that'll be faster than drawing them all in. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me recount that. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, and 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens here too. So answer choice C is the only one that has a different number, or 3. It's the only one that has a different number of hydrogens, so that is why it's a constitutional isomer. Which of the following are a valid set of resonance structures? Okay, so let's see. First thing I'm looking for is atoms are not moving. So all these atoms are in the same arrangement. Okay, C, these atoms are not in the same arrangement because the nitrogen has 2 oxygens directly bonded to it and a carbon, but over here it doesn't. So C I can eliminate immediately. So A or B is a good option, but not C. Now, let's see if I can make this resonance structure. So it looks like a pair of electrons move from here to here, making this bond. And then this one broke. And so that does seem like a valid set of Lewis structures to me. And then this one, it looks like same thing happened here. This set of electrons went over. So I think more than one of these is a valid resonance structure. I would say A and B both seem correct to me. Okay. Select all that apply. Which two of the following are the highest contributing resonance structures for the molecule in the box? Okay, so again, the first thing I'm looking for is, did any atoms change places? And based on that, I can tell that there's a hydrogen on this sulfur that wasn't there before. And so I'm getting rid of that one. Another thing is having two separations of charge like this isn't really good. It is just kind of unstable to have that. It's one of the rules of resonance. So if we're only allowed to have two good ones, this is probably not one because it is so much charge separation. So I'm going to see if these are both valid, then these will be the two highest contributors. If not, then I'll check to see if this one, number 1, is actually valid or not. So if I put my electrons here and then break this bond, that would give me this structure. So that is a valid resonance structure. If instead I put this here and break this bond, that would give me this. So that would be a valid resonance structure. So that, you can see how I very quickly was able to eliminate 2 just based on things I knew without having to even draw resonance structures. So even if you just had the rules of resonance structures memorized, you should have been able to get close to this one. So I'm going to give 2 and 3 as my top options. Okay, which of the following is a tertiary amine? So we're looking for a nitrogen with 3 carbons bonded to it. A nitrogen with 2 carbons and a hydrogen is a secondary, and a nitrogen with 1 carbon is a primary. So if we want a tertiary, that's this one. So this has 2 hydrogens, so that can't be right. This has 1 hydrogen, so that can't be right. This has 2 hydrogens, so that can't be right. So the answer is none of these are tertiary amines. Okay. Indicate which functional groups are present in this molecule. So typically I'll circle anything that's not plain hydrocarbon chain. So this, and this. So I see an alkene, an alcohol, and an aldehyde. So that's what I'm looking for. So there's no alkyne, I can eliminate that. There's no alkyne, I can eliminate that. So if you just knew that this double bond was called alkene, you could get rid of 2 of them. Now, we have a C double bond to O, so that could, in theory, be a ketone or an aldehyde. But if you know that with that hydrogen bonded to it, it's an aldehyde, then you can eliminate this ketone and that ketone. And you can get to the right answer without even having to know if the alcohol is primary, secondary, or tertiary. But we'll see, we look at the point of attachment right here, and it's bonded to 2 things, so that is a secondary alcohol. Which molecule would you expect to have the lowest boiling point based on intermolecular forces? Okay, so less intermolecular forces equals lower boiling point. So looking at this one, the first thing I'm going to do is say what intermolecular forces are present here. All of them obviously have dispersion forces, so that doesn't help us much here. This one has dipole-dipole. This one would have H bonding because this OH is it's like a super dipole, so there's a strong dipole moment here. Same thing here, this would have H bonding. This would have H bonding, and this would have H bonding. So the only one without hydrogen bonding is going to have the weakest intermolecular forces. So weakest intermolecular force is going to be the lowest boiling point. I'm going to just double check that's what it asked. Yep. Okay, so that's going to be answer choice A. Rank the following from most acidic to least acidic. So the first thing I'm going to look at is, are all these the same acidic atoms? And yeah, we have the same functional group in all of them. So this is where the pKa table doesn't help you. You have to be able to think about what else could there be. So are there additional resonance structures on any of them? Or is there inductive effect stabilizing them? And so when I look at these, I notice that several of them have an electronegative atom drawn to it, which means we have some of the induction. I'm just thinking, is that the right word for that? Inductive effect? I think it is. Sorry, I've just been so tired that my brain is not, is kind of feeling tired. I just want to make sure that I think it's called the inductive effect, where it pulls electron density away from it. We just talked about a similar concept in my OCHEM 2 class today that's slightly different. And I'm worried that I am mixing up those words, but I can't connect the dots. So just got to hope that that's right. So all of these have electronegative atoms attached equally far away. So their impact on the, if you lost that hydrogen and these became negative, the impact on the hydrogen would be, I guess I'll go all the way back to say, when I'm thinking about acidity, I'm thinking about the most acidic is most able to give up a proton, aka accept the electron pair that's left behind. In other words, it can handle the electrons left behind. So either resonance structures helps you do that. So all of these, if they lost their hydrogen and became negative, they all have a resonance structure. They all have the same one. So that isn't something that comes into play. So the next thing we can think of is if there is an electronegative atom on down the line, it's going to be pulling electron density towards itself and leave behind a partial positive, which then these electrons would be happy to give up those extra electrons to, so that oxygen's not too negative. So the more electronegative is better. So with fluorine being the most electronegative, fluorine is going to have the greatest impact on the inductive effect. So that is going to be the number one most acidic. Then we'll just go on down the line. So chlorine should be next. So that would be number 2. The next would be bromine. That would be number 3. The next would be iodine. That would be number 4. And the least acidic would be one that doesn't have the inductive effect at all. So that would be number 1. Okay, so hopefully that is helpful. Identify the base and conjugate base. Okay, so when I really think of acids first. So acid is the thing that loses a proton. So our HCl becomes Cl minus, so that lost a proton, so this is the acid. Our OH become OH2 plus, that makes this the base. Once the base gains a proton, then it becomes a conjugate acid. And once an acid loses its hydrogen, it becomes the conjugate base. So if I'm identifying the base and the conjugate base, that is 2 and 4. So these are all acid with 1, so I can get rid of all of them. So 2 and, let's see. We also know they won't be on the same side, so 3 and 4 doesn't make sense. So these are the only 2 options that make sense. So even if you couldn't identify the acid and the base, you should have been able to eliminate at least these 2 right here and here, just because you know that the conjugate acid and or base and conjugate base can't be on the same side. And then we decided that 2 was our base, so that's why we're getting rid of 1, and then our conjugate base is 4, so that is this answer choice. Okay, so next we're going to rank the bolded hydrogen from most acidic to least acidic. So for this type of question, we actually went over this in the review. I'm circling the bolded hydrogen. I'm going to say what functional group these are part of. So this is a carboxylic acid. This is just off of a regular old alkane chain. This is off an oxygen that's protonated. This is an alcohol. And this is an alkene. So you can go and look on your pKa table I gave you at the beginning for these. So the first one is an alkane. We have is at 50. I know we had carboxylic acid. Those are usually around 5. We had a protonated alcohol. Let's see. I think it was similar to this with 2 R groups. So that's around -3. I don't remember what else we had. An alkene, I think. That's around 44. So I have a lot of these memorized just off the top of my head to make these questions go faster, but I don't think you have to memorize them. I think if you can use the chart, that's great. So a carboxylic acid, that's going to be around 4.75. An alkane, that's going to be around 50. A protonated alcohol, we learned that was like around -3. A regular old alcohol, I'll just say off the top of my head, it's usually 16 to 18. And alkenes are usually 44. So on this thing, the most acidic is going to be the lowest pKa or the smallest pKa. So that is going to be 3. So I'm going to eliminate anything that doesn't have 3 as the most acidic. And then the least acidic is going to be this 50, so 2. Both of those have 2. Okay, so then let's see, what's the next most acidic? We already got 3 and 2. 5 is going to be next. Oh, those are the same, so you have to know the difference between these two. So let's see, between those, we have a 4 and a 16.8. So we said that this one would be the most acidic, with 4.75, and then 16 to 18 for 4. So even though if you couldn't get it down to just those two, sorry, I just put my iPad down. Even if you couldn't narrow it down between those two, if you can eliminate the ones you know are definitely wrong, you'll be able to get yourself to a closer chance just by guessing, like 50-50 instead of 20% chance. Okay, how many bonds in the structure below are formed by the overlap of 2 sp2 orbitals? So this is sp3, sp3, sp2, sp2, and this is sp3. Nope, yeah, okay. We went over in the review how to identify those hybridizations. So if you need to look back at that, look at the class review. My voice is starting to hurt, so or my throat is starting to hurt with talking, so that's why I'm not going to go over it too much in detail. But that means that the bonds that are formed by the overlap of 2 sp2, there's only 2 sp2 here and here. These overlap, so there's just one bond here that forms from the overlap. Which of the following is a ketone? Well, ketones have this carbonyl group and then an R group on either side. So with the alcohol, that becomes the carboxylic acid. This has our key structure in 2 R groups, so that's probably it. But I'm going to keep looking just in case. This has a hydrogen on one side and an oxygen on the other, so that's an ester. Even if it was an ester, from the hydrogen be an aldehyde, so that's not it. This has hydrogen on each side, so that's an aldehyde. That's actually formaldehyde, which they use in preserving bodies. If you've ever done any like pre-med lab thing, you might have used formaldehyde or been exposed to it. And this is an alcohol, no carbonyl at all. So our right answer is answer choice B. Okay, for the reaction below, predict which of the reaction is favored. So you gotta, this is an acid-base reaction. It's the only kind of reaction we learned. And so to predict, you need to identify the acid and the conjugate acid. So the acid is the one that loses a proton. So it goes from hydrogen to no hydrogen. Lost a proton, so this is the acid. Once the acid loses a proton, that's the conjugate base. This over here, this hydrogen, sodium is our base. So once the hydrogen gains a proton, it becomes the conjugate acid. So if we compare the acid and the conjugate acid, the reaction is going to favor the weaker acid because less reactive is favored in organic chemistry. So if you go to your pKa table, you would find that the pKa of this is about 4.7. The pKa of this, I think, is like 35. So the weaker acid is the larger pKa. So this side would be favored. So when you're answering this, you should have said something like, the right side is favored. You got 5 points for getting that right. And then your explanation should have been because reactions favor the weaker acid. I'm not going to keep writing. My voice hurts, so I'm going to try to go quickly. Because reactions favor the weaker acid or the weaker side. And when comparing the pKa, we know that H2 is a weaker acid than carboxylic acid. So if you got the right side, I gave you 5 points. And if you gave the full explanation, I gave you 5 more. But if you just said it's a weaker acid, but you didn't reference how you knew that it was a weaker acid, that's not a complete explanation. So I only gave you partial credit for that. Okay, for the reactions below, the arrow that's given is incorrect. Explain what's wrong with the arrow and describe the correct curved arrows. So I gave you 5 points for saying that the arrow should have gone from here to here because you didn't have to say why, but because, I guess you kind of did because you had to explain what was wrong. But you had to go from here to here because we should go from negative to positive. So if you explained that and clearly described why, you got 5 points for the explanation and 5 points for the correction. But a lot of you stopped there, but actually... if you had just drawn that, if a lot of you just put that, I'm going to show you what that would make. And then a bond to that hydrogen. But hydrogen can't have 2 bonds. So one more bond would have to break. And so you'd need a curved arrow here. So it was 5 points for that third curved arrow as well. For an explanation that had to break as well. Okay, the condensed formula for carboxylic acid. So you only had to do the carboxylic acid. So that has a CH3, a CH2, a CH2, a carbon with 2 oxygens, and a hydrogen. So if you accidentally lost one of these carbons or, like one carbon group, I just took off 1 point. A lot of you also wrote CH3, CH2, CH2, CO2H, that's fine. That's the same thing. But if you lost a carbon or added a hydrogen or something, you got points off. And then if you did, that's the condensed formula, but if you accidentally just did the molecular formula, C4H, 3, 4, 5, 6, 7, 8, O2, then I gave you like 3 points, I think, out of 5, or 2 points maybe out of 5. I think that was 2 points, and then there's 3 points if you made 2 mistakes here but got close, and then 4 points if you made 1 mistake. And then if it was perfect, you got all 5. Okay, what's the hybridization of the carbon? So the key here is make sure you know how to identify hybridization. So 1, 2, 3 areas of electron domain. So that's sp2. Again, we went over that in the review. You're really just looking for areas of electron density. So these are both sp2 hybridized. So both carbons are sp2. The following molecule is, both of these chlorines are very electronegative and they're pulling on the same side, so it is polar. They don't cancel one another out. Is this molecule cis, trans, or neither? You would not, if you drew a line right through the middle, the chlorines are on the same side, they're cis, because it's a double bond, you can't flip it around. And then the shape of the carbon atoms is 1, 2, 3 things bonded to them, so trigonal planar. All right. And then for the bonus question, I forgot to draw what that looked like. Let me go check, actually. I think I can look on Canvas for, let's see, maybe, let me pull that up really quickly for Canvas on the assignments. I had the picture in there originally, but I think I made an edit to it and accidentally deleted it itself. Exam 1, extra credit. So you're supposed to draw all the resonance structures for this. Okay, so I think I can do that real quick. Looks like okay. Okay, that's what we're looking at. So the first thing, I'm just going to start with areas of extra electron density. So I'm going to pull that bond up here. Make this O minus. So now it has several there, 3 lone pairs there, and then a positive charge. These are still here. So what a lot of people did is they didn't go step by step. So make sure you're going step by step. I mentioned this in my lectures, but in general, I'm not going to ask you to do anything with more than 1 charge separation. So, like, you don't have to do every individual, like, if a lone pair breaks up into a positive and a negative, you don't have to do that for every individual one, giving, like, multiple positives or negatives. You just have to do, at most, like, 1 charge separation. So you don't have to fill every single one in. But you do have to do every intermediate structure with just 1 separation of charge. I can show an example of what I mean. Okay, so these were all the Lewis structures that I was looking for. So what I saw some people do is they would take this one and they would do this, and then they would do a positive charge here and a negative charge here and a positive charge here. But see how there's 2 pluses and 2 minuses? That is very unfavorable. It's very unlikely to happen. So because that's not likely to happen, I wasn't grading for that. If you included them, I didn't count off, but you should have had each of these major structures with just 1 charge separation. And then a lot of people didn't have the brackets quite right. Technically, they're supposed to be like this, but if you do it like that, that's fine too on the last one, as long as it's in line with the arrows. And a lot of people also didn't have the double-headed arrows. These are what the resonance arrows look like, or you didn't have your curved arrows correct. Okay, well, that's it. I hope that was helpful. Please let me know if you